Hello and welcome to our comprehensive course on generating AI applications. My name is Alex, and I'll be one of your instructors throughout this journey. In this first lesson, we're going to explore the exciting world of AI apps and what makes them so powerful and transformative in today's digital landscape. Let's start by defining what an AI app is. An AI application, or AI app, is a software program that incorporates artificial intelligence technologies to perform tasks that typically require human intelligence. These tasks can include understanding natural language, recognizing patterns in data, making predictions, generating content, and learning from experience. What sets AI apps apart from traditional software is their ability to adapt and improve over time. While conventional applications follow predetermined rules and logic, AI apps can learn from data, identify patterns, and make decisions based on that learning. This makes them incredibly powerful for solving complex problems that would be difficult or impossible to address with traditional programming approaches. Let's look at some examples of AI apps that are changing the way we live and work. First, consider virtual assistants like Siri, Alexa, and Google Assistant. These apps use natural language processing to understand spoken commands and respond intelligently. They can set reminders, answer questions, control smart home devices, and much more. Another category is recommendation systems. When you watch Netflix and see personalized movie suggestions, or when Amazon recommends products based on your browsing history, you're experiencing AI in action. These systems analyze vast amounts of data about user behavior to predict what you might be interested in. In the healthcare sector, AI apps are being used to analyze medical images, predict disease outcomes, and even assist in drug discovery. For example, AI-powered diagnostic tools can examine X-rays and MRI scans to detect abnormalities that might be missed by the human eye. In the financial industry, AI apps are used for fraud detection, algorithmic trading, credit scoring, and customer service chatbots. These applications can process enormous amounts of transaction data in real time to identify suspicious patterns and prevent fraudulent activities. Content creation is another exciting area. AI apps can now generate text, create images, compose music, and even produce videos. Tools like GPT-based writing assistants help content creators draft articles, while AI image generators can create artwork from text descriptions. In transportation, self-driving cars represent one of the most ambitious applications of AI technology. These vehicles use computer vision, sensor fusion, and machine learning to navigate roads, avoid obstacles, and make split-second decisions. The common thread among all these examples is that they leverage AI to solve real-world problems in ways that were previously impossible or impractical. They can handle complexity, scale to massive datasets, and continuously improve their performance. Now, let's discuss the key components that make up an AI application. First, there's the data layer. AI apps require data to learn and make predictions. This data can come from various sources, such as user interactions, sensors, databases, or external APIs. The quality and quantity of data directly impact the performance of your AI app. Second, there's the model layer. This is where the AI magic happens. Machine learning models are trained on data to recognize patterns and make predictions. These models can range from simple linear regression to complex deep neural networks, depending on the problem you're trying to solve. Third, there's the application layer. This is the user-facing part of your AI app, the interface through which users interact with your AI capabilities. Could be a web application, mobile app, chatbot, or API endpoint. Finally, there's the infrastructure layer. This includes the servers, databases, and cloud services that host and run your AI application. Modern AI apps often require significant computational resources, especially during the training phase. Understanding these components is crucial because they form the foundation of any AI application you'll build. In the upcoming lessons, we'll dive deeper into each of these areas and learn how to work with them effectively. Before we wrap up this lesson, let's talk about why now is such an exciting time to be building AI apps. The field has experienced tremendous growth in recent years, driven by several factors. First, we have access to more data than ever before. The digital transformation of businesses and the proliferation of connected devices have created vast datasets that can be used to train AI models. Second, computational power has increased dramatically while costs have decreased. Cloud computing platforms now offer affordable access to powerful GPUs and specialized AI hardware, making it possible for individual developers and small teams to build sophisticated AI applications. Third, the AI development ecosystem has matured significantly. We now have robust frameworks, pre-trained models, and comprehensive tools that simplify the development process. You don't need to be a PhD researcher to build effective AI applications anymore. Fourth, there's growing demand for AI solutions across industries. Businesses are actively seeking ways to leverage AI to improve efficiency, enhance customer experiences, and gain competitive advantages. This creates abundant opportunities for AI app developers. As we progress through this course, you'll gain hands-on experience with the tools, techniques, and best practices needed to build your own AI applications. Whether you're interested in creating chatbots, recommendation systems, image recognition apps, or any other AI-powered solution, this course will provide you with the foundational knowledge and practical skills you need. In our next lesson, my colleague Sarah will guide you through the AI app development lifecycle, where you'll learn about the stages involved in bringing an AI application from concept to production. Thank you for your attention, and I look forward to continuing this journey with you.
Hello, everyone. I'm Sarah, and I'll be guiding you through this lesson on the AI app development lifecycle. In this lesson, we'll dive deep into the key stages of development from planning and design to testing and deployment. You'll learn about the unique challenges and considerations that come with building AI-powered applications and how to navigate them successfully. The AI app development lifecycle is similar to traditional software development in many ways, but it also has some distinct characteristics that set it apart. Understanding this lifecycle is crucial for managing your projects effectively and delivering successful AI applications. Let's start with the first stage, problem definition and planning. This is where you clearly define what problem you're trying to solve and determine whether AI is the right solution. Not every problem requires AI, and it's important to evaluate whether the complexity and cost of an AI solution are justified. During this stage, you should ask yourself several key questions. What specific problem are you trying to solve? What would success look like? Do you have access to the data you need? What are the constraints in terms of time, budget, and resources? What are the ethical considerations? Taking time to thoroughly answer these questions will save you significant effort later in the development process. Once you've defined the problem, the next stage is data collection and preparation. As Alex mentioned in the previous lesson, data is the foundation of any AI application. In this stage, you'll identify data sources, collect relevant data, and prepare it for use in training your models. Data preparation is often one of the most time-consuming parts of AI development. It involves cleaning the data to remove errors and inconsistencies, handling missing values, transforming data into appropriate formats, and sometimes augmenting your dataset to improve model performance. Industry experts often say that data scientists spend 80% of their time on data preparation and only 20% on actual modeling, which underscores how critical this stage is. The third stage is model selection and development. This is where you choose the appropriate machine learning algorithms for your problem and begin training your models. The choice of model depends on various factors, including the type of problem you're solving, the amount and type of data you have, the required accuracy, and the computational resources available. For example, if you're building a classification system to categorize customer feedback, you might start with simpler models like logistic regression or decision trees before moving to more complex approaches like neural networks. The key is to start simple and increase complexity only when necessary. During model development, you'll train your model on a portion of your data, tune its parameters to optimize performance, and validate it on a separate dataset to ensure it generalizes well to new, unseen data. This iterative process of training, evaluation, and refinement is at the heart of AI development. The fourth stage is model evaluation and validation. This is where you rigorously test your model to ensure it meets your performance requirements and behaves as expected. You'll use various metrics depending on your problem type. For classification problems, you might look at accuracy, precision, recall, and F1 score. For regression problems, you might examine mean squared error or R-squared values. But evaluation goes beyond just looking at numbers. You also need to test your model with real-world scenarios, check for biases that might lead to unfair outcomes, and ensure it performs well across different segments of your user population. This stage often reveals issues that need to be addressed before deployment. The fifth stage is integration and development of the application layer. Once you have a well-performing model, you need to integrate it into an actual application that users can interact with. This involves building the user interface, creating APIs for model serving, implementing business logic, and connecting to databases and other services. This stage requires collaboration between data scientists who built the models and software engineers who specialize in application development. The goal is to create a seamless experience where the AI capabilities are smoothly integrated into the overall application. The sixth stage is testing and quality assurance. This includes both traditional software testing and AI-specific testing. You'll test the user interface, API endpoints, database interactions, and error handling, just as you would with any software application. But you'll also need to test how the AI model performs in production-like conditions, how it handles edge cases, and how it responds to unexpected inputs. The seventh stage is deployment. This is where you make your AI application available to users. Deployment can take various forms depending on your application. You might deploy to cloud platforms like AWS, Google Cloud, or Azure. You might containerize your application using Docker for easier deployment and scaling, or you might deploy to edge devices for applications that need to run locally. Deployment also involves setting up monitoring and logging systems to track your application's performance, implementing security measures to protect user data and prevent unauthorized access, and creating backup and disaster recovery procedures. The eighth and final stage is monitoring and maintenance. Unlike traditional software, AI applications require ongoing attention even after deployment. You need to monitor model performance over time, watch for data drift where the characteristics of incoming data change, retrain models periodically with new data, and update your application based on user feedback and changing requirements. Model performance can degrade over time as their real-world conditions change. For example, a fraud detection model trained on historical data might become less effective as fraudsters develop new techniques. Regular monitoring helps you catch these issues early and take corrective action. Now, let's discuss some unique challenges in AI app development. First, there's the challenge of data quality and availability. AI models are only as good as the data they're trained on. If your data is biased, incomplete, or low quality, your model will reflect those issues. Obtaining high-quality, representative data can be difficult and expensive. Second, there's the challenge of model interpretability. Many powerful AI models, especially deep learning models, are black boxes that make it difficult to understand why they make specific predictions. This can be problematic in domains like healthcare or finance where you need to explain decisions. Third, there's the challenge of computational resources. Training complex AI models can require significant computational power and time. You need to balance model complexity with practical constraints around time and cost. Or there's the challenge of keeping up with rapid technological change. The field of AI is evolving quickly, with new techniques, frameworks, and best practices emerging constantly. Staying current requires ongoing learning and adaptation. Fifth, there are ethical and regulatory challenges. AI applications can have significant impacts on people's lives, and you have a responsibility to ensure your applications are fair, transparent, and respect user privacy. Depending on your industry and location, you may also need to comply with regulations around data protection and algorithmic decision-making. Despite these challenges, the AI app development lifecycle provides a structured approach to building successful applications. By following this lifecycle and being mindful of the unique aspects of AI development, you can navigate these challenges effectively. Let me share some best practices for each stage. In the planning stage, involve stakeholders early and often. Start with a minimum viable product rather than trying to build everything at once, and be realistic about timelines and resources. In the data stage, invest time in understanding your data thoroughly, document your data sources and preparation steps for reproducibility, and consider privacy and security from the beginning. In the modeling stage, start with simple models before moving to complex ones. Use version control for your code and models, and document your experiments and results. In the evaluation stage, use multiple metrics to get a complete picture of performance, test with diverse data to ensure fairness, and involve domain experts in evaluation. In the integration stage, designed for scalability from the start, implement proper error handling and fallback mechanisms, and create clear APIs for model serving. In the testing stage, automate testing wherever possible, test with realistic data and scenarios, and perform load testing to ensure your application can handle expected traffic. In the deployment stage, use gradual rollouts to catch issues early, implement comprehensive monitoring, and have a rollback plan in case of problems. In the maintenance stage, establish regular retraining schedules, monitor for data drift and model degradation, and continuously gather user feedback for improvements. As you progress through this course, you'll get hands-on experience with each of these stages. You'll learn not just the theory, but practical techniques for executing each stage effectively. In the next lesson, Alex will introduce you to the tools and platforms that will help you implement this lifecycle. You'll learn about frameworks like TensorFlow and PyTorch, cloud platforms, and other essential tools in the AI Developers Toolkit. Thank you for your attention, and I'll see you in future lessons.
Welcome back. This is Alex again. Now that you have a good understanding of the AI app development lifecycle from Sarah's lesson, it's time to explore the tools and platforms that will help you bring your ideas to life. In this lesson, we'll take a comprehensive look at the AI development ecosystem, including popular frameworks, cloud platforms, and essential tools that every AI developer should know about. Let's start with machine learning frameworks. These are software libraries that provide the building blocks for creating AI models. They handle the complex mathematics and computational operations behind the scenes, allowing you to focus on designing and training your models. TensorFlow is one of the most popular frameworks, developed by Google. It's an open-source platform that supports both research and production deployment. TensorFlow offers flexibility and scalability, making it suitable for everything from simple models to complex deep learning systems. It includes TensorFlow Lite for mobile and embedded devices, and TensorFlow.js for running models in web browsers. The framework has a large community, extensive documentation, and numerous pre-trained models you can use as starting points. PyTorch is another leading framework, originally developed by Facebook. It's particularly popular in the research community because of its dynamic computation graph, which makes it more intuitive and easier to debug. PyTorch has gained significant traction in recent years and is now widely used in both research and production environments. It offers excellent support for GPU acceleration and has a growing ecosystem of tools and libraries built around it. Keras is a high-level neural networks API that can run on top of TensorFlow, making it easier to build and train deep learning models. It's designed to be user-friendly and allows for rapid prototyping. If you're new to deep learning, Keras is an excellent starting point because it abstracts away much of the complexity while still giving you the power of TensorFlow underneath. Scikit-learn is essential for traditional machine learning tasks. While TensorFlow and PyTorch focus on deep learning, Scikit-learn provides implementations of classic algorithms like decision trees, random forests, support vector machines, and clustering algorithms. It's perfect for problems that don't require deep learning and offers simple, consistent interfaces for all its algorithms. For natural language processing, there are specialized tools like Hugging Face Transformers, which provides thousands of pre-trained models for tasks like text classification, named entity recognition, question answering, and text generation. Spacy is another excellent library for NLP, offering fast and efficient text processing capabilities. For computer vision, OpenCV is the go-to library. It provides tools for image and video processing, including object detection, face recognition, and image transformation. Combined with deep learning frameworks, OpenCV enables powerful computer vision applications. Now let's talk about cloud platforms. These platforms provide the infrastructure and services needed to develop, train, and deploy AI applications at scale. They eliminate the need to invest in expensive hardware and allow you to pay only for what you use. Amazon Web Services offers a comprehensive suite of AI and machine learning services. Amazon SageMaker is their flagship machine learning platform, providing tools for building, training, and deploying models. It includes built-in algorithms, support for popular frameworks, and automated model tuning. AWS also offers specialized services like Amazon Recognition for image and video analysis, Amazon Comprehend for natural language processing, and Amazon Lex for building conversational interfaces. Google Cloud Platform is another major player. Google AI Platform provides end-to-end machine learning services, from data preparation to model deployment. Given Google's expertise in AI, their platform offers cutting-edge capabilities. They also provide specialized APIs for vision, language, translation, and speech. Google Colab is a free service that provides Jupyter notebooks with free GPU access, making it great for learning and experimentation. Microsoft Azure offers Azure Machine Learning, a comprehensive platform for the entire machine learning lifecycle. It includes automated machine learning capabilities that can help you build models even if you're not an expert. Azure also provides cognitive services for vision, speech, language, and decision-making. Their platform integrates well with other Microsoft tools and services, which can be advantageous if you're already in the Microsoft ecosystem. For development environments, Jupyter notebooks have become the standard for data science and machine learning work. They allow you to combine code, visualizations, and explanatory text in a single document, making them perfect for exploratory analysis and sharing your work with others. Most cloud platforms provide managed Jupyter notebook services. Visual Studio Code has emerged as a popular code editor for AI development. It supports multiple programming languages, has excellent extensions for Python and data science, and integrates well with version control systems. PyCharm is another excellent IDE, specifically designed for Python development, with strong support for scientific computing and data science workflows. For version control, Git is essential. It allows you to track changes to your code, collaborate with others, and maintain different versions of your projects. GitHub, GitLab, and Bitbucket are popular platforms for hosting Git repositories. For AI projects, you also need to version your datasets and models, not just your code. Tools like DVC, Data Version Control, and MLflow help with this. Speaking of MLflow, it's an open-source platform for managing the machine learning lifecycle. It helps you track experiments, package code into reproducible runs, and share and deploy models. As your AI projects grow in complexity, tools like MLflow become invaluable for maintaining organization and reproducibility. For data storage and management, you'll need databases and data warehouses. PostgreSQL and MySQL are popular relational databases. MongoDB is a leading NoSQL database for unstructured data. For big data scenarios, you might use Hadoop or Apache Spark. Cloud platforms offer managed database services that handle scaling and maintenance for you. Docker has become essential for deploying AI applications. It allows you to package your application and all its dependencies into containers that can run consistently across different environments. This solves the "it works on my machine" problem and makes deployment much more reliable. Kubernetes is used for orchestrating containers at scale, automatically handling deployment, scaling, and management of containerized applications. For API development, Flask and FastAPI are popular Python frameworks. They make it easy to create REST APIs that expose your AI models to other applications. FastAPI is particularly well-suited for machine learning applications because of its automatic API documentation and high performance. Monitoring and logging are crucial for production AI applications. Tools like Prometheus and Grafana help you monitor system metrics and visualize performance. For application logging, the ELK stack, Elasticsearch, Logstash, and Kibana is widely used. Cloud platforms also provide their own monitoring and logging services. For data visualization and exploration, libraries like Matplotlib, Seaborn, and Plotly allow you to create charts and graphs to understand your data and communicate results. Tableau and Power BI are powerful tools for creating interactive dashboards and reports. Now, let's discuss how to choose the right tools for your project. The choice depends on several factors. Consider your team's expertise and experience. If your team is already familiar with certain tools, that can be a strong reason to use them. Consider the specific requirements of your project. Some frameworks are better suited for certain types of problems. Consider your deployment environment. If you're deploying to mobile devices, you'll need tools that support that. Consider your budget. While many tools are open source and free, Cloud services and some commercial tools have costs. Consider community and support. Tools with large, active communities tend to have better documentation, more tutorials, and quicker bug fixes. For beginners, I recommend starting with Python as your programming language, as it's the most widely used language in AI. Use scikit-learn for traditional machine learning and Keras with TensorFlow for deep learning. Start with Google Colab for your development environment, as it's free and requires no setup. Use GitHub for version control. As you gain experience, you can explore more advanced tools and platforms. For production applications, you'll want to use robust cloud platforms like AWS, Google Cloud, or Azure. Implement proper CI/CD pipelines for automated testing and deployment. Use Docker and Kubernetes for containerization and orchestration. Implement comprehensive monitoring and logging. Use managed services where possible to reduce operational overhead. It's also important to stay updated with new tools and technologies. The AI field evolves rapidly, and new tools emerge regularly. Follow AI blogs and newsletters, participate in online communities like Reddit's machine learning subreddit or AI-focused Discord servers, attend conferences and meetups, and take online courses to learn new tools and techniques. Let me share some practical advice for working with these tools. Start simple and add complexity gradually. Don't try to learn everything at once. Focus on mastering the basics of a few key tools before expanding your toolkit. Read the documentation. It might seem obvious, but thoroughly reading the official documentation can save you hours of troubleshooting. Look for tutorials and examples. Most popular tools have extensive tutorials and example projects that can help you learn. Experiment with different tools. The best way to learn is by doing. Build small projects to try out different frameworks and platforms. Join communities. Engaging with other developers can accelerate your learning and help you solve problems. Before we wrap up, let's talk about the importance of choosing the right tool for the job. It's tempting to use the latest, most advanced tools for every project, but that's not always the best approach. Sometimes a simple solution is better than a complex one. A logistic regression model that you can train in minutes might be sufficient for your problem, rather than a deep neural network that takes hours to train. Similarly, you might not need a full Kubernetes cluster for a simple application that could run on a single server. The key is to understand your requirements and constraints, then choose tools that best meet those needs. As you gain experience, you'll develop intuition for which tools are appropriate for different situations. In our next lesson, Sarah will guide you through setting up your development environment. You'll get hands-on experience installing and configuring the tools we've discussed, and you'll be ready to start building your first AI application. Thank you for your attention, and I look forward to seeing you in the next module.
Hello, everyone. Sarah here again. Welcome to Module 2, where we'll start building our first AI application. This is where theory meets practice, and you'll get hands-on experience with the tools and techniques we've discussed. In this lesson, we'll walk through the process of setting up your development environment. We'll cover installing the necessary software, configuring your tools, and making sure you have everything you need to start coding. A well-configured environment is crucial for a smooth development process. So let's get started. Before we begin installing anything, let's talk about what we need and why. Your development environment is your workspace, and just like a physical workspace, having the right tools organized properly makes all the difference in your productivity and effectiveness. For AI development, we need several key components. First, we need Python, which is the primary programming language for AI and machine learning. Most AI frameworks and libraries are built with Python, and it has become the de facto standard in the field. Second, we need a package manager to install and manage Python libraries. We'll use pip, which comes with Python, and possibly conda for managing environments. Third, we need an integrated development environment or code editor where we'll write our code. Fourth, we need the actual AI and machine learning libraries like TensorFlow, scikit-learn, and others. Fifth, we need Jupyter Notebook for interactive development and experimentation. And finally, we need Git for version control. Let's start with installing Python. If you're on Windows, go to python.org and download the latest version of Python 3. Make sure to check the box that says Add Python to Path during installation. This is important because it allows you to run Python from any command prompt. If you're on macOS, Python might already be installed, but it's often an older version. I recommend installing Python 3 using Homebrew, a package manager for macOS. You can install Homebrew by following the instructions on brew.sh, then run brew install Python 3. If you're on Linux, Python is usually pre-installed, but you can install or update it using your distribution's package manager, like apt on Ubuntu or yum on CentOS. After installing Python, open a terminal or command prompt and type Python version or Python 3 version to verify the installation. You should see the version number displayed. If you see an error, you may need to troubleshoot your path settings. Next, let's set up virtual environments. Virtual environments are isolated Python environments that allow you to install packages for specific projects without affecting your system-wide Python installation. This is crucial because different projects might require different versions of the same library, and virtual environments prevent conflicts. Python comes with a built-in tool called Ven for creating virtual environments. To create a virtual environment, navigate to your project directory and run python m-ven-mynv, where mynv is the name of your environment. You can name it anything you like. To activate the environment on Windows, run mynv /scripts/activate. On macOS and Linux, run source mynv bin activate. When activated, you'll see the environment name in your command prompt. Now, any packages you install will be installed only in this environment. Alternatively, many developers use Anaconda or Miniconda, which provide Conda as both a package manager and environment manager. Conda is particularly popular in data science because it handles not just Python packages, but also system-level dependencies. To install Anaconda, download it from anaconda.com and follow the installation instructions. Miniconda is a lighter version that includes just Conda and Python. With Conda, you create environments using Conda create and myinnova Python equals 3.9 and activate them with conda activate myinnova. Now let's install the essential libraries. With your virtual environment activated, you can install packages using pip. Let's start with the core data science libraries. Run pip install numpy pandas matplotlib seaborn. NumPy provides support for large multidimensional arrays and matrices, along with mathematical functions. Pandas offers data structures and analysis tools, particularly for working with tabular data. Matplotlib and Seaborn are visualization libraries for creating charts and graphs. Next, install scikit-learn for traditional machine learning. Pip install scikit-learn. This gives you access to a wide range of machine learning algorithms and utilities. For deep learning, you'll want to install TensorFlow and Keras. Run pip install TensorFlow. This will install both TensorFlow and Keras, as Keras is now integrated into TensorFlow. If you have a compatible NVIDIA GPU and want to leverage GPU acceleration, you'll need to install the GPU version and set up CUDA, but for learning purposes, the CPU version is sufficient. If you prefer PyTorch, install it with pip install torch vision. The installation command might vary depending on your system and whether you want GPU support, so check the PyTorch website for the specific command for your setup. For natural language processing, install the transformers library, pip install transformers. You might also want to install Spacy, pip install Spacy, and then download a language model like Python n Spacy download n core web _sm. For computer vision beyond deep learning, install OpenCV, pip install OpenCV Python. Now let's set up Jupyter Notebook. Install it with pip install Jupyter. Once installed, you can start Jupyter by running Jupyter Notebook in your terminal. This will open a web browser with the Jupyter interface, where you can create and run notebooks. Jupyter Notebooks are incredibly useful for AI development because they allow you to write code in cells, run them individually, and see results immediately, including visualizations. Alternatively, you might want to use Jupyter Lab, which is a more advanced interface. Pip install Jupyter Lab and start it with Jupyter Lab. For your code editor, I highly recommend Visual Studio Code. Download it from code.visualstudio.com and install it. Once installed, add some essential extensions. Open VS Code, go to the Extensions view by clicking the square icon in the sidebar, and search for and install the Python extension by Microsoft. This provides IntelliSense, linting, debugging, and other features for Python development. Also install the Jupyter extension, which allows you to work with Jupyter notebooks directly in VS Code. You might also want the Pilots extension for enhanced Python language support. Configure VS Code to use your virtual environment. Open the command palette with Ctrl-Shift-P or Command-Shift-P, type Python, select Interpreter, and choose your virtual environment from the list. This ensures VS Code uses the correct Python installation and has access to the packages you've installed. Now let's set up Git for version control. Download Git from gitscm.com and install it. After installation, you need to configure it with your name and email. Open a terminal and run git config globaluser.name your name and git config globaluser.email your.email at example.com. These details will be attached to your commits. Create a GitHub account if you don't have one already. GitHub is the most popular platform for hosting Git repositories and collaborating on code. Once you have an account, you can create repositories to store your projects. VS Code has built-in Git support, making it easy to commit changes and push to GitHub. Let's talk about organizing your project structure. A well-organized project makes development easier and more maintainable. Here's a typical structure for an AI project. Create a main project folder with your project name. Inside, create a data folder for your datasets, with subfolders like raw for original data and processed for cleaned data. Create a notebooks folder for Jupyter notebooks used for exploration and experimentation. Create a circ folder for your source code organized into modules. Create a models folder to save trained models. Create a tests folder for unit tests. Include a requirements.txt file listing all your dependencies, which you can generate with pipfreeze requirements.txt. Include a readme.md file describing your project. And include a .gitignore file to specify which files Git should ignore, like data files and model files that are too large for version control. Now let's verify everything is working. Create a new Python file or Jupyter notebook and try importing the libraries we installed. Run import numpy as np, import pandas as pd, import matplotlib.pyplot as plt, import matplotlib.pyplot as plt, import tensorflow as tf. If all of these imports work without errors, your environment is set up correctly. Let's also do a quick test of TensorFlow. Run this simple code print tf.__version__ to see the TensorFlow version, and print GPU available tf.config.list_physical_devices GPU to check if GPU support is available. Even if you don't have a GPU, TensorFlow will work fine on CPU for learning purposes. Let me share some troubleshooting tips for common issues. If you get command not found errors, check your path environment variable to ensure Python and other tools are included. If package installations fail, try upgrading pip with pip install upgrade pip. If you encounter permission errors on Linux or macOS, you might need to use pip install user or fix your Python installation permissions, but avoid using sudo with pip as it can cause issues. If you have conflicts between packages, try creating a fresh virtual environment. If TensorFlow or PyTorch installations fail, check the official documentation for your specific system requirements and installation commands. For Windows users, if you encounter issues with certain packages that require compilation, you might need to install Microsoft C++ build tools. The error message will usually tell you if this is needed. Now, let's talk about some best practices for maintaining your development environment. First, always use virtual environments for your projects. This prevents dependency conflicts and makes your projects reproducible. Second, keep a requirements.txt file updated with all your dependencies. This allows others or your future self to recreate the environment easily. Third, regularly update your packages to get bug fixes and new features, but be cautious with major version updates that might break compatibility. Fourth, document any special setup steps in your project README. Fifth, Use .getignore to avoid committing large files or sensitive information to version control. Consider using Docker for even more reproducible environments. Docker allows you to package your entire environment, including the operating system, Python, and all dependencies, into a container. This ensures that your code runs identically on any machine. While Docker adds some complexity, it's invaluable for production deployments and team collaboration. If you're working in a team, consider using tools like Poetry or pipenv for dependency management. These tools provide more sophisticated dependency resolution and lock files that ensure everyone on the team has exactly the same package versions. For cloud-based development, consider using platforms like Google Colab, which provides free Jupyter notebooks with pre-installed libraries and free GPU access. This is great for learning and experimentation without setting up anything locally. However, for serious development work, having a local environment gives you more control and flexibility. As you progress in your AI development journey, you might want to set up additional tools. Consider installing a database like PostgreSQL for data storage. Consider setting up Docker for containerization. Consider using MLflow for experiment tracking. Consider setting up a local instance of Jupyter Hub if you're working with a team. But for now, the environment we've set up is more than sufficient to start building AI applications. Before we move on, let's create a simple test project to make sure everything works together. Create a new folder for your project, set up a virtual environment, create a Jupyter notebook, and write a simple script that loads a dataset, performs some basic analysis, and creates a visualization. This will confirm that all the pieces of your development environment are working together properly. Congratulations! You now have a fully functional AI development environment. You have Python installed, essential libraries ready to use, Jupyter for interactive development, a powerful code editor in VS Code, and Git for version control. You're now ready to start building AI applications. In the next lesson, Alex will guide you through creating your first AI application. You'll apply what you've learned and build something real. Make sure your environment is set up and working before moving on. If you encountered any issues during setup, take time to resolve them now, as we'll be building on this foundation. Thank you for your attention, and I'll see you in the next lesson.
Welcome back. This is Alex, and now for the fun part. In this lesson, we will build a simple AI application from scratch. We will choose a practical use case, a sentiment analysis tool, and walk through the entire process of building it. You will learn how to load a pre-trained model, process input data, and generate predictions. By the end of this lesson, you will have a working AI application to be proud of. Sentiment analysis is the process of determining whether a piece of text expresses positive, negative, or neutral sentiment. It's widely used in business to analyze customer feedback, social media monitoring, brand reputation management, and market research. It's an excellent first project because it demonstrates key AI concepts while being practical and relatable. Let's start by understanding what we're building. Our sentiment analysis application will take text input, such as a product review or a tweet, and predict whether the sentiment is positive or negative. We'll use a pre-trained model, which means we don't need to train a model from scratch. This is a common approach in AI development, as pre-trained models can save enormous amounts of time and computational resources. First, let's set up our project. Create a new folder called Sentiment Analyzer. Inside this folder, create a virtual environment as Sarah showed you in the previous lesson. Activate the virtual environment, and we'll install the necessary packages. For this project, we'll use the Transformers library from Hugging Face, which provides access to thousands of pre-trained models. We'll also need Torch or TensorFlow as the backend. Let's install them. Pip install Transformers Torch. We'll also install some utilities. Pip install pandas numpy. Now, let's create a new Python file called sentiment_analyzer.py. Open it in your code editor and let's start coding. First, we need to import the necessary libraries. At the top of your file, write from Transformers import pipeline. The pipeline function is a high-level API that makes it easy to use pre-trained models for common tasks. Now, let's load a pre-trained sentiment analysis model. Write sentiment_pipeline equals pipeline sentiment analysis. That's it. This single line loads a pre-trained model specifically designed for sentiment analysis. By default, it uses a model called Distilbert-based Unkist Fine-Tuned SST2 English, which has been trained on movie reviews but works well for general sentiment analysis. Let's test it with a simple example. Right. Result equals sentiment_pipeline. I love this product. It works great. Then print the result. Print result. Save your file and run it from the terminal. Python sentiment_analyzer.py. You should see output like label, positive, score, 0.9998. The model has classified the text as positive with very high confidence. Let's try a negative example. Add result equals sentiment_pipeline. This is terrible. I hate it. Print it and run again. You'll see it's classified as negative. Now let's make our application more interactive. We'll create a function that takes text input and returns a formatted result. Write a function, def_analyze_sentiment, text result equals sentiment_pipeline, text, 0, label equals result, label, score equals result, score, return f sentiment, label, confidence, score, 0.2%. Now we can call this function with any text, print, analyze_sentiment. The weather is beautiful today. Let's make it even more useful by analyzing multiple texts at once. The pipeline can handle lists of texts efficiently. Create a function, def_analyze_multiple. Text results equals sentiment_pipeline, texts, return, text, result, label, result, score, for text, result in zip, texts, results. Test it with multiple reviews. Reviews equals great product, waste of money. It's okay, nothing special. For text, label, score in analyze_multiple. Reviews print, f, text, dash, label, score, 0.2%. Now let's build a simple command line interface so users can interact with our application. We'll use Python's input function. Write def main, print, sentiment analysis tool, print, enter text to analyze or quit to exit. While true, text equals input greater than sign. If text.lower equals quit, break. If text.strip, print, analyze_sentiment, text. Else, print, please enter some text. Add the standard Python idiom to run the main function. If __name___ equals main. Now when you run your script, you'll have an interactive sentiment analysis tool. You can type any text, and it will tell you the sentiment. Let's enhance our application by adding the ability to analyze text from a file. This is useful when you have many reviews or comments to analyze. Create a function, def_analyze_file, file name import pandas as pd, df equals pd read_csv, file name, df, sentiment, equals df, text, dot apply, lambda x, sentiment_pipeline, x, 0, label, df, confidence, equals df, text, dot apply, lambda x, sentiment_pipeline, x, 0, score, return df. This function reads a CSV file with a text column, analyzes each text, and adds sentiment and confidence columns. Now let's talk about what's happening under the hood. When you call the pipeline, several steps occur. First, the text is tokenized, meaning it's broken down into tokens that the model can understand. Different models use different tokenization strategies. Second, the tokens are converted to numerical IDs based on the model's vocabulary. Third, these IDs are fed into the neural network model, which processes them through multiple layers. Fourth, the model outputs probabilities for each possible class, in this case positive and negative. Finally, these probabilities are converted into the label and score you see in the result. The model we're using, Distilbert, is a smaller, faster version of BERT, which stands for bidirectional encoder representations from transformers. BERT was a breakthrough in natural language processing because it learns context from both directions in a sentence, unlike previous models that only looked at text in one direction. DistillBERT retains 97% of BERT's performance while being 60% faster and 40% smaller. Let's explore some limitations and how to handle them. First, the model has a maximum input length, typically 512 tokens. If your text is longer, it will be truncated. For very long texts, you might need to split them into chunks or use a different approach. Second, the model was trained on specific types of text, primarily movie reviews. While it generalizes well, it might not perform as well on highly specialized domains like medical or legal text. Third, the model only classifies as positive or negative. Some texts might be neutral or mixed, but the model will still choose one of the two labels. Let's add error handling to make our application more robust. Wrap your sentiment analysis in a try-except block. Def analyze underscore sentiment underscore safe, text try. Result equals sentiment underscore pipeline, text, 0. Return F sentiment. Result, label, confidence. Result, score, colon 0.2%. Accept exception as E. Return F error analyzing text, str. Now let's make our application more sophisticated by adding support for different languages. The Transformers library has models for many languages. To use a multilingual model, specify it when creating the pipeline. Multilingual underscore pipeline equals pipeline, sentiment analysis. Model equals nulptown/BERT base multilingual uncast sentiment. This model works with English, Dutch, German, French, Spanish, and Italian, and it classifies sentiment on a 1 to 5 star scale instead of just positive/negative. Let's also add the ability to save results. Create a function that saves analysis results to a CSV file, def save underscore results. Texts, file name import pandas as PD. Results equals text, text, sentiment, sentiment underscore pipeline, text, 0, label, confidence, sentiment underscore pipeline, text, 0, score, 4 text in texts, df equals PD data frame, results, df.to underscore CSV, file name, index equals false, print, f results saved to file name. Now let's add some visualization to better understand the results. We'll create a simple bar chart showing the distribution of sentiments. Import matplotlib. Import matplotlib.pyplot as plt. Create a visualization function. Def visualize underscore sentiments. Text results equals sentiment underscore pipeline. Texts. Labels equals r. Label. 4 are in results. From collections import counter. Counts equals counter. Labels. plt.bar. Counts.keys. Counts.values, plt.title, sentiment distribution, plt.label, sentiment, plt.label, count, plt.show. Let's test our complete application with a real-world scenario. Imagine you're analyzing customer reviews for a product. Create a list of sample reviews and analyze them. Customer underscore reviews equals best purchase ever, broke after 1 week, good value for money. Not what I expected. Absolutely love it. Terrible quality. Works as described. Disappointed with this product. Visualize underscore sentiments. Customer underscore reviews. Now let's discuss how you could extend this application. You could add a web interface using Flask or FastAPI, making it accessible through a browser. You could integrate it with social media APIs to analyze tweets or comments in real time. You could add more sophisticated text preprocessing, like removing URLs, handling emojis, or correcting spelling. You could fine-tune the model on your specific domain data to improve accuracy for your use case. You could add support for aspect-based sentiment analysis, which identifies sentiment toward specific aspects of a product or service. Let's create a simple web API for our sentiment analyzer using Flask. First, install Flask, pip install Flask. Create a new file called app.py. Import Flask and our sentiment pipeline. From Flask import Flask, request, Johnify. From Transformers import pipeline, app equals Flask, underscore underscore name underscore underscore. Sentiment underscore pipeline equals pipeline, sentiment analysis. Create an API endpoint, Add app route /analyze, method sad-face post, def analyze, data equals request.get_JSON, text equals data.get text. If not text, return Johnify, error, no text provided. 400, result equals sentiment_pipeline, text. 0, return Johnify, text, sentiment. Result, label. Confidence, result, score. Add the code to run the app. If __name _equals app run, debug equals true. Now you can run Python app.py, and your sentiment analyzer will be available as a web API. You can test it using curl or Postman by sending a post request with JSON data. Let's talk about performance considerations. Loading the model takes time and memory. In a production application, you'd load the model once when the application starts, not for every request. For high-traffic applications, you might need to use batching to process multiple requests together, or deploy multiple instances behind a load balancer. You might also want to use model optimization techniques like quantization to reduce model size and increase speed. Before we finish, let's add proper documentation to our code. Good documentation makes your code maintainable and helps others understand how to use it. Add docstrings to your functions explaining what they do, what parameters they take, and what they return. Let's also create a README file for our project. Create readme.md and document what the application does, how to install dependencies, how to run it, and provide usage examples. Good documentation is just as important as good code. Finally, let's add our project to version control. Initialize a Git repository, git init. Create a .gitignore file to exclude virtual environment and cache files. Add your files, git add. Commit, git commit, initial commit. Sentiment analysis application. If you want to share your project, create a repository on GitHub and push your code. Congratulations! You've built your first AI application. You've learned how to use pre-trained models, process text data, create an interactive interface, build a web API, and properly structure and document a project. This sentiment analyzer, while simple, demonstrates the core concepts you'll use in more complex AI applications. The skills you've learned here, loading models, processing data, making predictions, and exposing functionality through APIs, are fundamental to AI application development. As you continue learning, you'll build on these foundations to create more sophisticated applications. In the next lesson, Sarah will show you how to deploy your application so others can use it. You'll learn about different deployment options and best practices for making your AI application production ready. Thank you for following along, and I hope you're excited about what you've built.
Hello again. Sarah here. Congratulations on building your first AI app in the previous lesson. Now it's time to share it with the world. In this lesson, you'll learn how to deploy your application to make it accessible to users. We'll explore different deployment options from simple hosting services to more advanced cloud platforms. We'll also discuss important considerations like scalability and security, ensuring your app is ready for production. Deployment is a critical phase in the AI app development lifecycle. A great application that nobody can access isn't very useful. The goal of deployment is to make your application available, reliable, secure, and performant for your users. Let's start by understanding the different deployment options available. The choice depends on your application's requirements, your technical expertise, your budget, and your expected user load. The simplest option is running your application on your local machine. This is fine for development and testing, but it's not suitable for production because your computer needs to be always on and connected to the internet. You're exposing your personal computer to security risks, and you can't handle significant traffic. However, for quick demos or personal projects, tools like ngrok can temporarily expose your local server to the internet. The next step up is deploying to a virtual private server, or VPS. Services like DigitalOcean, Linode, and Vultr provide affordable virtual machines where you have full control. You rent a server, install your software, and run your application. This gives you complete control, but also complete responsibility for security, updates, and maintenance. Platform as a Service, or PaaS, solutions like Heroku, Google App Engine, and Azure App Service abstract away server management. You push your code and the platform handles deployment, scaling, and infrastructure. This is great for getting started quickly without worrying about server administration. For containerized applications, you might use container orchestration platforms like Kubernetes or managed container services like Amazon ECS, Google Cloud Run, or Azure Container Instances. These are more complex but offer excellent scalability and flexibility. Serverless platforms like AWS Lambda, Google Cloud Functions, and Azure Functions allow you to run code without managing servers at all. You pay only for the compute time you use. This works well for applications with variable or unpredictable traffic. For AI applications specifically, there are specialized platforms like Hugging Face Spaces, Streamlit Cloud, and Gradio, which are designed for deploying machine learning models with minimal configuration. Let's walk through deploying our sentiment analysis application using several different approaches. We'll start simple and progress to more sophisticated options. First, let's prepare our application for deployment. Create a requirements.txt file that lists all dependencies. You can generate this automatically by running pip freeze requirements.txt in your virtual environment. However, it's better to manually create a clean requirements.txt with only the packages you actually need: Transformers, Torch, Flask, Pandas, NumPy. This keeps your deployment lean and avoids unnecessary dependencies. Next, create a configuration file for your application. Instead of hard-coding settings like port numbers and debug mode, use environment variables. Modify your Flask app to read the port from an environment variable. Port equals int os.environ.get port 5000. Then run with app run. Host equals 0.0.0.0, port equals port. The host equals 0.0.0 makes your app accessible from outside your machine. Now let's deploy to Heroku, which is beginner-friendly and has a free tier. First, install the Heroku CLI from heroku.com. Create a Heroku account if you don't have one. Log in using Heroku Login. In your project directory, initialize a Git repository if you haven't already. Git init. Create a proc file which tells Heroku how to run your app. The proc file should contain web python app.py. Create a runtime.txt file specifying your Python version, Python 3.9.7. Commit your files, git add, and git commit on prepare for deployment. Create a Heroku app, Heroku create your app name. Push your code, git push Heroku main. Your app is now deployed. Heroku will provide a URL where you can access it. However, there's a problem with deploying AI models to Heroku's free tier. The slug size limit is 500 megabytes, and transformer models can be large. You might need to use a smaller model or upgrade to a paid tier. Alternatively, you could load the model from Hugging Face's Model Hub at runtime, though this increases startup time. Let's try deploying to Google Cloud Run, which is well suited for containerized AI applications. First, we need to containerize our application using Docker. Create a Docker file in your project directory. The Docker file should specify from Python 3.9 Slim as the base image, workdirectory app to set the working directory, copy requirements.txt. To copy the requirements file, run pip install no cached error or requirements.txt. To install dependencies, copy your application code, and cmd python app.py to specify the command to run your app. Build your Docker image. Docker build to sentiment analyzer. Test it locally. Docker run p5000:5000 sentiment analyzer. If it works, you're ready to deploy to Cloud Run. Install the Google Cloud SDK from cloud.google.com. Authenticate Cloud Auth Login. Create a project or select an existing one. Cloud config set project your project ID. Enable the necessary APIs. Cloud services enable or n.googleapis.com, and at cloud services enable container registry.googleapis.com. Build and push your container to Google Container Registry. Cloud build submit tag gcr.io/your-project-id/sentiment-analyzer. Deploy to Cloud Run. Cloud Run Deploy Sentiment Analyzer, image gcr.io/your-project-id/sentiment-analyzer, platform managed, region US Central 1 allow, unauthenticated. Cloud Run will provide a URL for your deployed application. Cloud Run automatically scales based on traffic, so you only pay for what you use. It can scale to 0 when there's no traffic, which is very cost-effective. However, this means the first request after a period of inactivity will be slow as the container starts up. For AI applications, this cold start can be significant because loading the model takes time. To reduce cold start times, you can use several strategies. Keep your Docker image small by using slim base images and only including necessary dependencies. Load your model efficiently, perhaps using a smaller or quantized version. Use Cloud Run's minimum instances setting to keep at least one instance always warm, though this costs more. Implement lazy loading where the model is loaded only when first needed, not at application startup. Now let's discuss deploying to AWS, which offers the most comprehensive set of services. For a simple deployment, you could use AWS Elastic Beanstalk, which is similar to Heroku. For more control, you could use EC2 instances. For containerized applications, use ECS or EKS. For serverless, use Lambda. Though Lambda has limitations for AI applications due to package size limits and execution time limits. A popular approach for AI applications on an AWS is using SageMaker, which is specifically designed for machine learning. You can deploy your model as a SageMaker endpoint, which handles scaling, monitoring, and model management. However, SageMaker has a steeper learning curve and can be more expensive than other options. Let's talk about deployment best practices. First, use environment variables for configuration. Never hard-code API keys, database passwords, or other sensitive information. Use environment variables or secret management services. Second, implement proper logging. In production, you need visibility into what's happening. Use structured logging and send logs to a centralized service like CloudWatch, Stackdriver, or a third-party service like Loggly. Third, implement health checks. Your deployment platform needs to know if your application is healthy. Create an endpoint like /health that returns a 200 status code when everything is working. Fourth, use HTTPS. Always encrypt traffic between users and your application. Most platforms provide free SSL certificates through Let's Encrypt. Security is crucial for production applications. Implement authentication if your API shouldn't be publicly accessible. Use API keys, OAuth, or JWT tokens. Implement rate limiting to prevent abuse. Libraries like Flask Limiter make this easy. Validate and sanitize all inputs. Never trust user input. Implement cores properly if your API will be called from web browsers. Keep dependencies updated to patch security vulnerabilities. Use tools like pip audit to check for known vulnerabilities. Monitoring and observability are essential. You need to know how your application is performing and when things go wrong. Monitor key metrics like request rate, response time, error rate, CPU and memory usage, and model inference time. Set up alerts for anomalies like error rate spikes, slow response times, or high resource usage. Use application performance monitoring tools like New Relic, Datadog, or open-source alternatives like Prometheus and Grafana. For AI-specific monitoring, track model performance metrics. Is your model's accuracy degrading over time? Are you seeing data drift where incoming data differs from training data? Are there biases in predictions across different user segments? Tools like Evidently, AI and Labs can help with ML-specific monitoring. Let's discuss scaling. As your user base grows, you need to handle more traffic. There are two types of scaling, vertical and horizontal. Vertical scaling means using a more powerful server with more CPU, RAM, and GPU. This is simple but has limits and can be expensive. Horizontal scaling means using multiple servers and distributing traffic among them. This is more complex but can scale indefinitely. For horizontal scaling, you need a load balancer to distribute traffic across multiple instances of your application. Most cloud platforms provide load balancing services. Your application needs to be stateless, meaning each request is independent and doesn't rely on data stored in memory from previous requests. Any state should be stored in a database or cache that all instances can access. For AI applications, model serving can be a bottleneck. Loading a large model into memory on each instance is wasteful. Consider using a dedicated model serving solution like TensorFlow Serving, TorchServe, or Triton Inference Server. These are optimized for serving ML models at scale. Alternatively, use a managed service like AWS SageMaker, Google AI Platform, or Azure Machine Learning for model deployment. Caching can significantly improve performance. If multiple users are likely to request predictions for the same input, cache the results. Use Redis or Memcached for caching. However, be careful with caching predictions, as you need to invalidate the cache when you update your model. Let's talk about continuous deployment. Manually deploying every time you make a change is tedious and error-prone. Set up a CI/CD pipeline to automate testing and deployment. When you push code to your repository, automated tests run. If tests pass, the code is automatically deployed to production. Tools like GitHub Actions, GitLab CI, Circle CI, and Jenkins can help with this. A typical CI/CD pipeline for an AI application includes running unit tests for your code, running integration tests for your API, validating your model's performance on a test dataset, building a Docker image, pushing the image to a container registry, and deploying to your hosting platform. You may also want to implement blue-green deployment or canary deployment to minimize risk when deploying changes. Let's create a deployment checklist. Before deploying to production, ensure you have removed all debug code and verbose logging, set debug mode to false, configured environment variables for all settings, implemented proper error handling, added authentication and authorization, implemented rate limiting, set up HTTPS, created a health check endpoint, configured logging to a centralized service, set up monitoring and alerts, created backups of any data, did set up monitoring and alerts, created backups of any data, keep backups of any data, chief graph. And they're again created up with any backups of any data. Super logging. Treated backups of any data. Prepared a rollback plan in case something goes wrong. After deployment, monitor closely for the first few hours or days. Check logs for errors, monitor performance metrics, verify that all features work as expected, and be ready to roll back if issues arise. For model updates specifically, consider A/B testing where a portion of traffic goes to the new model while the rest uses the old model. Compare performance before fully switching over. This is called shadow deployment or canary deployment. Documentation is crucial. Document your deployment process so others on your team can deploy or so you can remember how to deploy in 6 months. Document your API endpoints so users know how to interact with your application. Use tools like Swagger or Postman to create interactive API documentation. Finally, let's discuss compliance and legal considerations. Depending on your application and users, you might need to comply with regulations like GDPR for European users, CCPA for California residents, or HIPAA for healthcare data. Ensure you have proper data handling, privacy policies, and user consent mechanisms. Congratulations! You now understand the deployment landscape for AI applications. You've learned about different deployment options, from simple platforms like Heroku to sophisticated container orchestration with Kubernetes. You've learned about security, monitoring, scaling, and best practices for production applications. Deployment might seem daunting at first, but start simple. Deploy to a platform like Heroku or Cloud Run to get something working quickly. As you gain experience and your requirements grow, you can move to more sophisticated solutions. In the next module, Alex will guide you through advanced topics in AI app development. You'll learn about integrating with external APIs, working with data effectively, and scaling your applications. Thank you for your attention, and congratulations on completing Module 2.
Welcome to Module 3. This is Alex, and we're now entering the advanced section of our course. In this lesson, we're going to explore how to integrate your AI apps with external APIs. APIs, or application programming interfaces, allow your app to connect with other services and access their data and functionality. We'll look at how to find and use APIs and how to incorporate them into your AI apps to create more powerful and versatile tools. APIs are the connective tissue of modern software. They allow different applications and services to communicate with each other, share data, and combine functionality in powerful ways. For AI applications, APIs open up endless possibilities. You can access real-time data, integrate with existing platforms, leverage specialized services, and create rich, interconnected experiences. Let's start by understanding what APIs are and how they work. An API is a set of rules and protocols that defines how software components should interact. Most modern web APIs use REST, which stands for Representational State Transfer, or GraphQL, a more recent query language for APIs. REST APIs use HTTP methods like GET to retrieve data, POST to create new data, PUT or patch to update data, and delete to remove data. They typically exchange data in JSON format, which is easy for both humans and machines to read and write. When you make an API request, you send an HTTP request to a specific URL called an endpoint with optional parameters and data. The API processes your request and sends back a response, usually containing the data you requested or a status message. For example, to get weather data, you might send a GET request to api.weather.com/current?city=London and receive back JSON data with temperature, humidity, and other weather information. Let's explore some categories of APIs that are particularly useful for AI applications. Weather APIs like OpenWeatherMap and Weather API provide current weather, forecasts, and historical data. This is useful for applications that need to consider weather conditions. Financial APIs like AlphaVantage, Yahoo Finance, and various cryptocurrency APIs provide stock prices, market data, and financial news. Social media APIs from Twitter, Reddit, Facebook, and Instagram allow you to access posts, comments, and user data. This is valuable for sentiment analysis, trend detection, and social listening applications. News APIs like News API and Google News provide access to news articles from thousands of sources. This is useful for staying current with events or analyzing news trends. Natural language APIs like Google Cloud Natural Language, AWS Comprehend, and Azure Text Analytics provide advanced NLP capabilities that you can combine with your own models. Computer vision APIs like Google Cloud Vision, AWS Recognition, and Azure Computer Vision can analyze images and videos. Translation APIs like Google Translate and DeepL can translate text between languages. Speech APIs like Google Speech-to-Text and Azure Speech Services can transcribe audio or generate speech. There are also specialized AI model APIs. OpenAI provides access to powerful language models like GPT. Hugging Face offers thousands of pre-trained models through their inference API. Anthropic, Cohere, and other companies provide AI capabilities through APIs. Using these APIs, you can incorporate state-of-the-art AI capabilities without training models yourself. Now let's learn how to work with APIs in Python. The requests library is the standard tool for making HTTP requests. If you don't have it installed, run pip install requests. Let's start with a simple example using a public API that doesn't require authentication. We'll use JSON placeholder, a fake REST API for testing. Import requests. Import requests. Make a GET request. Response equals requests.get https://JSON placeholder typicode.com/posts/1. Check if the request was successful. If response.status_code equals 200, data equals response.json. Print data. The status code 200 means success. The JSON method parses the JSON response into a Python dictionary. Let's try a more practical example with a weather API. We'll use OpenWeatherMap, which has a free tier. First, sign up at openweathermap.org and get an API key. Store your API key securely. Never hardcode API keys in your code. Use environment variables. Import OS, API_key equals OS, environ, get openweather_API_. Make a request. City equals London. URL equals fhttp://api.openweathermap.org/data/2.5/weather. Q equals city, and APID equals API_key, and units equals metric. Response equals requests get URL. Parse the response. If response.status_code equals 200, data equals response.json. Temperature equals data, main, temp. Description equals data, weather, 0, description. Print, weather in city. Temperature, degree C, description. Now let's integrate this into an AI application. Imagine you're building a travel recommendation system that considers current weather. You could fetch weather data for different destinations and use it as a feature in your recommendation model. Or you could build a chatbot that answers weather questions by calling the Weather API when needed. Let's look at handling API errors. Network requests can fail for many reasons. The server might be down, your internet connection might be unstable, you might have exceeded rate limits, or your API key might be invalid. Always implement error handling. Try. Response equals requests to get URL, timeout equals 10, response.raise_for_status, data equals response.json, accept requests to exceptions, timeout, print, request timed out, accept requests.exceptions.http error as e, print, fhttp error, e, accept requests.exceptions, request exception as e, print, f error, e. Many APIs require authentication to identify who's making requests and to enforce rate limits. Common authentication methods include API keys, which are simple tokens you include in your request, either in the URL, in a header, or in the request body. OAuth is a more complex but secure method used by many social media APIs. It involves a multi-step process to get an access token. JWT tokens are JSON Web Tokens used for authentication in many modern APIs. Basic authentication uses a username and password, though this is less common for modern APIs. Let's look at an example using API key authentication in a header. Headers equals authorization. fbearer API_key. Content type application/JSON. Response equals requests. Get URL. Headers equals headers. Rate limiting is important to understand. Most APIs limit how many requests you can make in a given time period. Exceeding these limits will result in errors, typically a 429 status code. To handle rate limits, implement exponential backoff, where you wait progressively longer between retries. Use caching to avoid making the same request multiple times. If you need high request volumes, consider upgrading to a paid API tier. Monitor your usage to stay within limits. Let's implement a simple rate limiter. Import time. From FuncTools import wraps, def rate_limit, max per minute interval equals 60.0/max per minute. Def decorator. Func last called equals 0.0. At wraps, func, def wrapper, *args. Corgs elapsed equals time.time. Last_called 0. Left_wait equals min_interval elapsed. If left_0. Time.sleep. Left_. Ret equals func, args, corgs. Last_called 0 equals time.time. Return ret, return wrapper, return decorator. Now you can decorate your API call functions at rate_limit 60. Def call_API, URL return requests, get URL. Let's build a practical example. An AI-powered news summarizer. We'll use News API to fetch recent articles and a summarization model to create summaries. First, get an API key from newsapi.org. Install the necessary libraries. Pip install requests transformers. Create a function to fetch news. Def fetch_news. Topic, API_key URL equals FHTTPS://newsapi.org/v2/everything. Q equals topic and API key equals API underscore key and pages eyes equals 5. Response equals requests get URL. If response.status underscore code equals 200, return response.json articles. Return, create a function to summarize text. From transformers import pipeline, summarizer equals pipeline, summarization, model equals Facebook/BartLarge CNN, def summarize underscore text, text, max underscore length equals 130 if len, text, less than 100, return text. Summary equals summarizer, text, max underscore length equals max underscore length, min underscore length equals 30, do underscore sample equals false. Return summary, 0, summary underscore text. Combine them, def get underscore news underscore summaries, topic, API underscore key articles equals fetch underscore news, topic, API underscore key. Summaries equals, for article and articles, title equals article, title, content equals article, content, or article, description, or, if content. Summary equals summarize underscore text, content, summaries.append, title, title, summary, summary, URL, article, URL, return summaries. Now let's discuss working with post requests which are used to send data to APIs. For example, to create a new resource, data equals title, my post, body. This is the content, user ID. 1. Response equals requests.post. https://JSON placeholder. typicode.com/post single quote. JSON equals data. The JSON parameter automatically converts your Python dictionary to JSON and sets the appropriate content type header. Let's look at a more advanced example. Integrating with the OpenAI API to add powerful language capabilities to your application. Install the OpenAI library, pip install OpenAI. Set up the client. From OpenAI import OpenAI. Client equals OpenAI, API equals OS, environ, get, open underscore API underscore, make a request. Response equals client.chat.completions.create, model equals GPT-4, messages sad face, role, user, content. Explain quantum computing in simple terms. Answer equals response.choices 0.message.content, print, answer. You could integrate this into a chatbot, a content generation tool, or any application that needs advanced language understanding. For example, you could build a customer service bot that uses your sentiment analyzer to detect frustrated customers and uses GPT to generate empathetic, helpful responses. Let's discuss API design considerations for your own applications. If you're building an AI application that others will use, you might want to expose your functionality through an API. Good API design includes using clear, consistent naming conventions, providing comprehensive documentation, implementing proper error handling with meaningful error messages, using appropriate HTTP status codes, implementing authentication and rate limiting, versioning your API so you can make changes without breaking existing users, and providing examples and SDKs in popular programming languages. Let's create a simple API wrapper class to make working with an API cleaner. Class weather API. Def underscore underscore init underscore underscore self API underscore key self dot API underscore equals API underscore self base underscore URL equals http://API openweathermap.org/data/2.5 def get underscore current underscore weather self city URL equals f self.base underscore URL/weather params equals q city apid self.api underscore key units metric response equals requests.get URL params equals params response.raise underscore for underscore status return response.json def get underscore forecast self city days equals 5 URL equals f self.base underscore URL/forecast params equals q city apid self.api_key, units, metric, CNT, days *8, response equals requests get, URL, params equals params, response.raise_for_status, return response.json. Now using the API is cleaner. Weather equals weather API, API_key. Current equals weather.get_current_weather, London. Forecast equals weather.get_forecast. London, days equals 3. Let's discuss webhooks, which are a way for APIs to push data to your application instead of you constantly polling for updates. With webhooks, you register a URL with a service, and when an event occurs, the service sends an HTTP post request to your URL with data about the event. This is more efficient than polling and enables real-time integrations. To use webhooks, you need a publicly accessible endpoint. You can create one using Flask at approute/webhook methods sadface post. Def webhook, data equals request.json. Hashtag process the webhook data, return 200. Register this URL with the service you're integrating with. Let's talk about API testing and debugging. Tools like Postman and Insomnia provide graphical interfaces for testing API requests. They're invaluable for understanding how an API works before writing code. For debugging, use logging to record all API requests and responses. Use try-except blocks to catch and log errors. Check API documentation carefully, as small mistakes in parameters or headers can cause failures. Monitor API status pages, as sometimes issues are on the API provider side, not yours. Let's discuss asynchronous API requests for better performance. When you need to make many API requests, doing them sequentially is slow. Asynchronous requests allow you to make multiple requests concurrently. Use the AIP library, pip install AIP. Here's an example. Import Asyncio, import AIP, async def fetch, session, URL async with session, get URL as response. Return await response.json, async def fetch _ URLs async with AIP.client session as session. Tasks equals fetch, session, URL for URL and URLs. Return await Asyncio, gather, *tasks, URLs equals URL1, URL2, URL3. Results equals Asyncio.run, fetch URLs. This can be much faster than sequential requests. Before we finish, let's discuss API costs and optimization. Many APIs charge based on usage. Monitor your costs carefully. Implement caching to avoid redundant requests. Use batch endpoints when available, as they're often more cost-effective than individual requests. Choose the right API tier for your needs. Sometimes a more expensive tier with higher limits is more cost-effective than paying overage fees. Consider building your own models for high-volume use cases, as API costs can add up quickly at scale. Let's also discuss API reliability and fallbacks. APIs can go down or become slow. Implement timeouts so your application doesn't hang waiting for a response. Implement retries with exponential backoff for transient failures. Have fallback options like using cached data or a secondary API. Monitor API performance and have alerts for when things go wrong. Finally, let's discuss legal and ethical considerations. Read the API's terms of service carefully. Some APIs restrict how you can use the data. Respect rate limits and don't try to circumvent them. Be mindful of user privacy when using APIs that handle personal data. Comply with regulations like GDPR when applicable. Give proper attribution if required by the API's terms. Congratulations! You now understand how to integrate external APIs into your AI applications. You've learned how to make API requests, handle authentication, manage errors, and build practical integrations. APIs dramatically expand what your AI applications can do, allowing you to access real-time data, leverage specialized services, and create rich, connected experiences. In the next lesson, Sarah will dive deep into working with data, covering collection, cleaning, pre-processing, and feature engineering. These skills are crucial for building high-quality AI models. Thank you for your attention, and I'll see you in the next lesson.
Hello, everyone. Sarah here. Data is the lifeblood of any AI application, and in this lesson, we'll explore how to work with data effectively. We'll cover data collection, cleaning, and pre-processing, as well as techniques for data augmentation and feature engineering. You'll learn how to handle different types of data, from text and images to structured and unstructured data. By the end of this lesson, you'll have the skills to prepare high-quality data for your AI models. The quality of your AI model is fundamentally limited by the quality of your data. There's a saying in machine learning, garbage in, garbage out. No matter how sophisticated your model is, if your data is poor quality, biased, or insufficient, your model will not perform well. That's why data work is so critical and why data scientists often spend the majority of their time on data-related tasks rather than modeling. Let's start with data collection. Where does data come from? There are many sources. Public datasets are available from repositories like Kaggle, UCI Machine Learning Repository, Google Dataset Search, and government open data portals. These are great for learning and prototyping. Web scraping allows you to collect data from websites. Tools like Beautiful Soup, ScrapPy, and Selenium can help. However, always check the website's terms of service and robots.txt file and respect rate limits. APIs, as Alex discussed in the previous lesson, provide structured access to data from various services. User-generated data comes from your own application's users. This is valuable because it's directly relevant to your use case. Sensors and IoT devices generate continuous streams of data. Purchased datasets are available from data brokers and specialized providers. Synthetic data is artificially generated data that mimics real data. This is useful when real data is scarce, expensive, or sensitive. When collecting data, consider several factors. Relevance. Is the data actually related to the problem you're trying to solve? Quantity. Do you have enough data to train a robust model? The amount needed varies by problem, but more is generally better. Quality. Is the data accurate, complete, and consistent? Representativeness. Does the data represent the full range of scenarios your model will encounter in production? Bias. Does the data contain systematic biases that could lead to unfair or inaccurate predictions? Legality and ethics. Do you have the right to use this data? Does it contain personal information that requires special handling? Let's talk about data formats. Structured data is organized in tables with rows and columns like CSV files or database tables. This is the easiest type to work with. Semi-structured data has some organization but isn't strictly tabular like JSON or XML. Unstructured data lacks predefined structure like text documents, images, audio, or video. Each type requires different handling approaches. Let's work with some real data. We'll use Pandas, the standard Python library for data manipulation. If you haven't installed it, run pip install pandas. Let's load a CSV file. Import pandas as pd, df equals pd read underscore csv, data.csv. Examine the first few rows. Print df.head. Get basic information. Print sf.info. Get statistical summaries. Print def.describe. Now let's talk about data cleaning, which is the process of identifying and correcting errors and inconsistencies. Common data quality issues include missing values, where some entries are blank or null, duplicates, where the same record appears multiple times, outliers, which are extreme values that might be errors or genuine but rare cases, inconsistent formatting, like dates in different formats, or text with varying capitalization, invalid values like negative ages or dates in the future, typos and errors in text data. Let's handle missing values. First, identify them. Print df.isNull.sum. This shows how many missing values each column has. We have several options for handling missing values. Drop rows with missing values. df_clean equals df.dropna. This is simple, but you lose data. Drop columns with too many missing values. df_clean equals df.dropna, axis equals 1, fresh equals len, df asterisk 0.5. This keeps columns where at least 50% of values are present. Fill with a constant value, df column equals df column dot fillna 0. Fill with statistical measures, df column equals df column dot mean. For numerical data, you might use mean, median, or mode. Fill using forward fill or backward fill, df column equals df column dot fillna method equals fill. This uses the previous or next valid value. Use interpolation df column equals df column dot interpolate. This estimates missing values based on surrounding values. Use advanced imputation methods like k-nearest neighbors or model-based imputation. The best approach depends on your data and use case. If data is missing completely at random and you have plenty of data, dropping might be fine. If there's a pattern to the missingness, you need to be more careful. Let's handle duplicates. Print df.duplicated.sum. Remove duplicates. df_clean equals df.drop duplicates. Sometimes you want to keep the first or last occurrence. df_clean equals df.drop duplicates. Keep equals last. Let's handle outliers. First, identify them. A common approach is using the interquartile range. Q1 equals df column.quantile 0.25, Q3 equals df column.quantile 0.75, IQR equals Q3 Q1, lower bound equals Q1 1.5 asterisk IQR, upper bound equals Q3 plus 1.5 asterisk IQR, outliers equals df column, route thous equals df column, Falf OIQR equals df column, Riedler equals df column, Thadwar, df. You can then remove outliers, cap them at the bounds, or investigate them individually. Sometimes outliers are errors, but sometimes they're legitimate extreme cases that are important to keep. Let's standardize text data. Convert to lowercase df text equals df text dot stir lower. Remove white space, df text equals df text dot str strip. Replace values, df category equals df category dot replace cat1 category 1, cat2 category 2. Let's handle date and time data. df date equals pd2 underscore datetime df date. Once converted to datetime, you can extract components. df year equals df date.dt, df month equals df date.dt month, df day underscore of week equals df date.dt day of week. Now let's talk about data transformation and preprocessing. This prepares data for machine learning models. Scaling brings numerical features to a similar range. Many algorithms perform better when features are scaled. Standard scaler standardizes features to have mean 0 and standard deviation 1 from slearn.preprocessing import standard scaler. Scaler equals standard scaler. df feature 1 feature 2 equals scaler.fit underscore transform. df feature 1 feature 2. Min max scaler scales features to a range typically 0 to 1. From slearn.preprocessing import min max scaler, scaler equals min max scaler, df feature 1 feature 2 equals scaler.fit underscore transform, df feature 1 feature 2. Encoding converts categorical variables into numerical format that models can use. Label encoding assigns each category a number. From slearn.preprocessing, import label encoder, equals label encoder, df category underscore transform, df category underscore transform, df category. This works for ordinal categories with a natural order. One-hot encoding creates binary columns for each category. df underscore encoded is stickmisms. Predict for encoded temmies a pisat phase category. This is better for nominal categories without inherent order. Feature engineering is the process of creating new features from existing data to improve model performance. This is often where domain expertise becomes crucial. For date features, extract components like year, month, day of week, hour, or create features like is_weekend or is_holiday. For text features, create features like text length, word count, presence of specific keywords, or sentiment scores. For numerical features, create polynomial features, ratios between features, or binned versions of continuous variables. For location data, calculate distances, create region categories, or extract features like urban versus rural. Let's create some engineered features. df text length equals df text.strlen. df word count equals df text.str_split.strlen. df price underscore per underscore unit equals df priced df quantity. df is the weekend equals df date.dt. dfweek.asin 5 3s. Now let's discuss working with text data specifically. Text preprocessing is crucial for NLP tasks. Common steps include lowercasing, text equals text.lower. Removing punctuation, import string, text equals text.translate. Stir make trans, string.punctuation. Removing numbers, text equals .join, char for char and text if not, char is to get. Tokenization, splitting text into words or tokens. Tokens equals text.split. Or use more sophisticated tokenization from nltk.tokenize import word tokenize. Tokens equals word tokenize. Tokens equals word tokenized. Text. Removing stop words, which are common words like the, is, at that don't carry much meaning. From nltk.corpus import stopwords.words. English, tokens equals word for word and tokens if word non and stop underscore words. Stemming reduces words to their root form. From nltk.stem, import porter stemmer. Stemmer equals porter stemmer. Tokens equals stemmer.stem, word for word and tokens. Lemmatization is similar but produces actual words. From nltk.stem import wordnet lematizer. Lematizer equals wordnet lematizer. Tokens equals lematizer.lematize, word for word and tokens. For using text in machine learning models, you need to convert it to numerical format. Bag of words counts word occurrences from sklearn.feature_extraction.text, import count. Vectorizer equals count vectorizer. X equals vectorizer.fit_transform text. TASFIDF weighs words by their importance from sklearn.feature_extraction.text, import TFIDF vectorizer. Vectorizer equals TFIDF. Vectorizer, X equals vectorizer.fit_transform text. Word embeddings like word2, vec, or glove represent words as dense vectors that capture semantic meaning. Transformer-based embeddings like BERT provide even more sophisticated representations. Let's discuss working with image data. Images need to be preprocessed before feeding to models. Resize images to a consistent size. From PIL import image, img equals image.open, image.jpg, img resized equals img.resize, 224 Normalize pixel values, typically to 0 to 1 range. Import numpy as np, img, array equals np.array, img, 255.0. Or normalize using ImageNet statistics for transfer learning. Mean equals np.array 0.485, 0.456, 0.406, std equals np.array 0.229, 0.224, 0.225, img normalized equals img underscore array mean /td. Data augmentation for images creates variations to increase dataset size. From tensorflow.keras.preprocessing.image, import image data generator. Data gen equals image data generator. Rotation range equals 20. Width underscore shift range equals 0.2. Height underscore shift range equals 0.2. Height underscore shift range equals 0.2. Horizontal flip equals true. Now let's talk about handling imbalanced data, which is when some classes have many more examples than others. This is common in real-world problems like fraud detection or disease diagnosis. Imbalanced data can cause models to be biased toward the majority class. Solutions include undersampling the majority class. From ivelearn._sampling import random undersampler. Rus equals random undersampler. X underscore resampled. Y resampled equals rus.fit. Resample X, Y. Oversampling the minority class. From mblearn.over_sampling import random oversampler. Rows equals random over sampler. X underscore resampled, Y resampled equals rows dot fit underscore resample X, Y. Smote creates synthetic examples of the minority class. From inblern.over sampling import smote, smote equals smote, X underscore resampled, Y underscore resampled equals smote dot fit underscore resample X, Y. Using passwords to penalize misclassification of minority class more heavily from SD linear underscore model import logistic regression. Model equals logistic regression. Class weight equals balanced. Let's discuss data splitting. You need to split your data into training, validation, and test sets. Training set is used to train the model. Validation set is used to tune hyperparameters and make decisions during development. Test set is used for final evaluation and should not be touched until the end. A common split is 70% training, 15% validation, 15% test, though this varies. Use scikit-learn's train test. For the one model selection, import train test as splits. X train X temp, Y train Y temp equals train test as split. XY test underscore CX equals 0.3. Random state equals 42. XY test underscore test. Y val, Y underscore test. Y val, Y test, Y val, Y underscore test. Y val, Y underscore test. Y val, Y underscore in. X val val. Y governor underscore test, Y val, Y underscore, equals day 2 X val, X attest, Y val. Y seekest, Y val, Y stuff seekest. For time series data, don't use random splitting as it breaks temporal order. Use sequential splitting where training data comes before validation and test data. Let's talk about data versioning. Just like code, data changes over time. You collect more data, fix errors, or update preprocessing. Data versioning helps you track these changes and reproduce results. Tools like DVC, Data Version Control, integrate with Git to version data. Store metadata about your data, when it was collected, how it was processed, what filters were applied. This documentation is crucial for reproducibility. Now let's discuss data pipelines. As your project grows, you'll want to automate data processing. Create functions for each step. Def load data file path, return PD, read as CSV, file path, def clean data, df equals df.dropna, df equals df.drop underscore duplicates, return df engineer equals df feature 1, df feature 2, return df preprocess underscore df preprocess underscore d2, return df preprocess underscore 2, return def preprocess underscored. Since GUF 2 into def preprocess, if you would have thought net underscore 2 with def preprocess underscore 2, chain them together. Df equals load underscore data, data.csv, df equals clean underscore data, df equals engineer features, df scalar equals preprocessed data, df save processed data and preprocessing objects, df.to underscore csv, processed underscore data.csv, index equals false, import joblib.dump, scalar.pkl. For production, consider using workflow orchestration tools like Apache Airflow, Prefect, or Luigi to manage complex data pipelines. Let's discuss data quality monitoring. In production, data can change over time, a phenomenon called data drift. Monitor incoming data for changes in distribution, missing values, or unexpected values. Set up alerts for anomalies. Regularly retrain models on fresh data. Finally, let's talk about ethical considerations in data work. Be aware of bias in your data. Historical data often reflects societal biases. Models trained on biased data will perpetuate those biases. Actively work to identify and mitigate bias. Respect privacy. Handle personal data responsibly. Use techniques like anonymization, pseudonymization, or differential privacy when appropriate. Comply with regulations like GDPR, CCPA, and industry-specific requirements. Be transparent about what data you collect and how you use it. Obtain proper consent from users. Congratulations! you now have a comprehensive understanding of working with data for AI applications. You've learned about data collection, cleaning, pre-processing, feature engineering, and handling different data types. These skills are fundamental to building successful AI applications. Remember, great models start with great data. In the final lesson of this course, Alex will discuss scaling your AI applications. You'll learn about performance optimization, handling large data sets, and building systems that can grow with your needs. Thank you for your attention, and I'll see you in the next lesson.
Welcome to the final lesson of our course. This is Alex, and in this lesson, we'll discuss how to scale your AI application to handle growing user demand. Scaling is a critical consideration for any successful app, and AI apps come with their own unique challenges. We'll explore strategies for optimizing performance, managing resources efficiently, and ensuring your app can handle increased traffic. We'll also look at monitoring and maintenance best practices to keep your app running smoothly. By the end of this course, you'll have all the knowledge you need to build, deploy, and scale professional AI applications. Scaling is about ensuring your application can handle growth. As you gain more users, process more data, or add more features, your system needs to grow with those demands. For AI applications, scaling presents unique challenges because machine learning models can be computationally expensive, especially deep learning models that require significant memory and processing power. Let's start by understanding the difference between vertical and horizontal scaling. Vertical scaling, also called scaling up, means using more powerful hardware. You upgrade to a server with more CPU cores, more RAM, or better GPUs. This is the simplest approach because your application doesn't need to change. However, there are limits to how much you can scale vertically, and it can become very expensive. Horizontal scaling, also called scaling out, means using more servers. Instead of one powerful server, you have many less powerful servers working together. This can scale almost indefinitely and is often more cost-effective. However, it requires your application to be designed to work across multiple machines. For AI applications, you need to consider several components when scaling. The model inference component is where predictions are made. This is often the bottleneck. The data processing component handles incoming data, pre-processing, and feature extraction. The API layer handles requests from users and routes them to the appropriate services. The database stores user data, model metadata, and results. The model training component updates models with new data, though this is often done offline. Let's talk about optimizing model inference, which is usually the most expensive operation. Model quantization reduces the precision of model weights from 32-bit floating point to 8-bit integers or even lower. This reduces model size and speeds up inference with minimal accuracy loss. Import TensorFlow as TF. Converter equals tf.light. TF-light converter. From model. Converter.optimizations equals tf.light. Optimized default. Quantized underscore model equals converter. Convert. Model pruning removes unnecessary connections in neural networks, making them smaller and faster. Import TensorFlow underscore model underscore optimization as tfmot. Pruning underscore schedule equals tfmot.sparsity caras. Polynomial decay. Initial underscore sparsity equals 0.0. Final underscore sparsity equals 0.5. Begin underscore step equals 0. End underscore step equals 1000. Model equals tfmot.sparsity.caras. Prune underscore low underscore magnitude. Model. Pruning underscore schedule equals pruning underscore schedule. Knowledge distillation trains a smaller model to mimic a larger model's behavior. The smaller model is faster but retains much of the larger model's performance. Using appropriate hardware is crucial. CPUs are general purpose and work for most models but can be slow for large models. GPUs are specialized for parallel computations and dramatically speed up deep learning inference and training. TPUs, or tensor processing units, are Google's specialized chips optimized for TensorFlow. They offer even better performance for certain workloads. Edge devices like smartphones or IoT devices can run optimized models locally, reducing latency and server costs. Batching requests can significantly improve throughput. Instead of processing one request at a time, collect multiple requests and process them together. This is more efficient because it better utilizes GPU resources. Import torch, def batch underscore predict, texts, model, tokenizer, batch underscore size equals 32 predictions equals, for I in range, 0, len, texts, batch underscore size batch equals texts, I plus batch underscore size. Inputs equals tokenizer, batch, return underscore tensors equals point, padding equals true, outputs equals model, asterisk asterisk inputs. Predictions.extend, outputs.logits.argmax, dim equals 1, dot to list, return predictions. However, batching introduces latency because you wait to accumulate a batch. You need to balance throughput and latency based on your requirements. Caching is another powerful optimization. If many users request predictions for the same input, cache the result. Import Redis, cache equals Redis, host equals localhost, port equals 6379, def predict underscore with underscore cache, text, model cache underscore key equals f prediction, hash, text, cached underscore result equals cached, get, cache underscore key. If cached underscore result, return cached underscore result equals model dot predict, text, cache.ctext, cache underscore e, 3600, result, return result. Be careful with caching predictions because cached results become stale when you update your model. Implement cache invalidation strategies. Model serving frameworks are designed specifically for deploying ML models at scale. TensorFlow serving is optimized for TensorFlow models and handles batching, versioning, and monitoring. Docker run P8501:8501. Name equals TF serving. Mount type equals bind. Source equals /path /to /model. Target equals /models /model. A model and equals thermal. T TensorFlow /serving. TorchServe is PyTorch's serving framework with similar capabilities. Torch Model Archiver. Model name my_model. Version 1.0. Model file model.py. Serialized file model.pth. Handler.py. TorchServe. Start. Model store model_store. Models my_model equals my_model.mar. Triton Inference Server from NVIDIA supports multiple frameworks and is highly optimized for GPU inference. Load balancing distributes traffic across multiple instances of your application. When you have multiple servers, a load balancer sits in front of them and routes each request to an available server. This ensures no single server is overwhelmed. Cloud platforms provide load balancing services. AWS Elastic Load Balancing, Google Cloud Load Balancing, Azure Load Balancer. For Kubernetes, use ingress controllers. You can also use software load balancers like Nginx or HAProxy. Autoscaling automatically adjusts the number of running instances based on demand. During high traffic, more instances are started. During low traffic, instances are shut down to save costs. Cloud platforms provide autoscaling. AWS Autoscaling, Google Cloud Autoscaler, Azure Autoscale. For Kubernetes, use Horizontal Pod Autoscaler, kubectl Autoscale Deployment MyApp, CPU percent equals 50, min equals 1, max equals 10. This maintains CPU usage around 50% by adding or removing pods. Database scaling is important if your application stores significant data. For read-heavy workloads, use read replicas. The primary database handles writes, and multiple replicas handle reads. For write-heavy workloads, consider database sharding, where data is partitioned across multiple databases. Use caching layers like Redis or Memcake to reduce database load. Consider NoSQL databases like MongoDB or Cassandra for certain use cases, as they're designed to scale horizontally. Asynchronous processing can improve responsiveness. For long-running tasks like model training or batch predictions, use task queues. The API accepts the request, adds it to a queue, and immediately returns. Background workers process tasks from the queue. From celery import celery, app equals celery, tasks, broker equals Redis, / localhost, 6379. At app task, def train_model. Data hashtag training logic, return result. Users can poll for results or be notified via webhooks when processing completes. Monitoring is crucial for scaled systems. You need visibility into what's happening across all your servers. Monitor system metrics like CPU usage, memory usage, disk I/O, and network traffic. Monitor application metrics like request rate, response time, error rate, and queue length. Monitor ML-specific metrics like model inference time, prediction distribution, and model accuracy on recent data. Use monitoring tools like Prometheus for metrics collection, Grafana for visualization, ELK Stack for log aggregation, or cloud platform monitoring services. Set up alerts for critical issues. If error rate spikes, response time increases significantly, or a server goes down, you need to know immediately. Configure alerts to notify you via email, Slack, PagerDuty, or other channels. Logging at scale requires special consideration. With many servers generating logs, you need centralized log aggregation. Use structured logging with JSON format for easier parsing. Import logging, import JSON. Logger equals logging.getLogger, logger.info, JSON.dumps, event, prediction, model, sentiment, latency, 0.05, result, positive. Send logs to centralized services like Elasticsearch, CloudWatch, or Stackdriver. Implement log sampling for high-volume systems to avoid overwhelming your logging infrastructure. Performance testing helps you understand your system's limits before problems occur in production. Load testing simulates normal expected load to verify the system handles it. Stress testing pushes the system beyond normal load to find breaking points. Soak testing runs at normal load for extended periods to find memory leaks or degradation. Use tools like Apache JMeter, Locust, or Gatling. From Locust import HTTP user, task, between, class my user, HTTP user wait underscore time equals between 1, 3. At task, def predict, self to client.post, /predict, JSON equals, text, test. Cost optimization is important as you scale. Monitor your cloud spending carefully. Use reserved instances or committed use discounts for predictable workloads. They're much cheaper than on-demand pricing. Use spot instances or preemptible VMs for fault-tolerant workloads like batch processing. They're very cheap but can be terminated at any time. Right-size your instances. Don't use more powerful instances than you need. Implement autoscaling to avoid paying for idle resources. Use serverless options like Lambda or Cloud Functions for variable workloads. Optimize your models to reduce compute requirements. Let's discuss multi-region deployment for global applications. Deploying in multiple geographic regions reduces latency for users around the world and provides redundancy if one region has issues. However, it adds complexity. You need to route users to the nearest region using DNS-based routing or Anycast. You need to synchronize data across regions if your application has state. You need to manage deployments across multiple regions. Cloud platforms provide tools for multi-region deployment. AWS Global Accelerator, Google Cloud CDN, Azure Traffic Manager. Content Delivery Networks, or CDNs, cache static assets at edge locations around the world. While AI model inference can't be cached this way, your application's front-end assets can be. This reduces load on your servers and improves user experience. Use CDN services like CloudFront, Cloudflare, or Fastly. Let's talk about model versioning and A/B testing in production. As you improve your models, you need to deploy new versions safely. Implement blue-green deployment where you maintain two environments. Blue is the current production version. Green is the new version. You deploy to green, test it, then switch traffic from blue to green. If issues arise, you can quickly switch back. Implement canary deployment where you gradually roll out the new version. Start by sending 5% of traffic to the new version. If metrics look good, increase to 10%, then 25%, then 50%, then 100%. Implement A/B testing to compare model versions. Route a portion of users to Model A and another portion to Model B. Compare their performance metrics to determine which is better. Shadow mode is useful for testing new models. The new model receives all requests, but its predictions aren't returned to users. You log its predictions and compare them to the production model. This lets you validate the new model with real traffic without risk. Let's discuss handling model updates. When you deploy a new model, you need to ensure a smooth transition. Use model versioning in your serving infrastructure. TensorFlow Serving and TorchServe support multiple model versions simultaneously. Implement graceful shutdown where old instances finish processing their current requests before shutting down. Warm up new instances by sending test requests before routing real traffic to them. This ensures models are loaded and caches are populated. Data pipelines at scale require special consideration. For large datasets, use distributed processing frameworks like Apache Spark. From PySpark.sql import Spark session. Spark equals Spark session. Builder.appName, data processing, .get or create. df equals spark.read.csv, large underscore dataset, CSV. Processed underscore df equals df filter, df value, 0, .group by, category, .count. For streaming data, use frameworks like Apache Kafka, Apache Flink, or cloud streaming services. Implement data partitioning to process data in parallel. Use columnar formats like Parquet for efficient storage and processing. Security at scale is crucial. Implement rate limiting per user or API key to prevent abuse. From Flask_limiter import limiter. Limiter equals limiter, app, _func equals lambda. Request.headers, get, API key. At app route, /predict. At limiter.limit, 100 per hour. Def predict, pass. Use API gateways to handle authentication, rate limiting, and request routing. They sit in front of your services and provide a unified entry point. Implement DDoS protection using services like Cloudflare or AWS Shield. Encrypt data in transit using HTTPS and in REST using encryption at the database level. Regularly update dependencies to patch security vulnerabilities. Implement security scanning in your CI/CD pipeline. Disaster recovery planning is essential. What happens if your database crashes, a region goes down, or you deploy a bad update? Implement regular backups of all critical data. Test your backup restoration process. Implement redundancy at every level. Multiple servers, multiple databases, multiple regions. Document incident response procedures. Who gets notified? What are the steps to diagnose and fix issues? Practice disaster recovery scenarios with game days or chaos engineering. Let's discuss team organization for scaled systems. As your application grows, you might need specialized roles. DevOps engineers handle infrastructure, deployment, and monitoring. ML engineers focus on model development and optimization. Back-end engineers build APIs and services. Data engineers build and maintain data pipelines. Site reliability engineers ensure system reliability and performance. Clear responsibilities and good communication are crucial. Documentation becomes increasingly important as systems grow complex. Document your architecture, deployment procedures, troubleshooting guides, and API specifications. Use tools like Confluence, Notion, or GitHub wikis. Keep documentation up to date as systems evolve. Finally, let's talk about the future of AI scaling. Serverless ML is emerging, where you don't manage any infrastructure. Edge AI deploys models to devices, reducing latency and server costs. Federated learning trains models across distributed devices without centralizing data. Model-as-a-service platforms handle all scaling concerns for you. These trends will continue to make AI more accessible and easier to scale. Congratulations! You've reached the end of our comprehensive course on generating AI applications. Over these 3 modules, you've learned about AI app fundamentals, the development lifecycle, tools and platforms, environment setup, building your first app, deployment, API integration, data handling, and scaling. You now have the knowledge and skills to build, deploy, and scale professional AI applications. Remember, building great AI applications is a journey. Start with simple projects and gradually take on more complex challenges. Keep learning as the field evolves rapidly. Join communities, contribute to open source, and share your knowledge with others. The AI revolution is just beginning, and you're now equipped to be part of it. Thank you for joining Sarah and me on this learning journey. We hope this course has inspired you and given you the confidence to build amazing AI applications. Good luck with your projects, and we can't wait to see what you create.